Right, the next of our extension 2 topics sort of leads on very nicely from complex numbers, because we've talked a bit about factorising with complex numbers and what have you, but it's the extension of the polynomials topic from extension 1. So first of all, let's look at factorising. Remember this key idea: if all the coefficients are real, then we know that the solutions or factors or roots will appear in conjugate pairs. Right? So that was an idea we saw back when we were looking at complex numbers. Now that has a consequence then. Every polynomial of degree n can be factorised as a mixture, again this is if the coefficients are real, as a mixture of quadratic and linear factors. Okay? So the linear factors would be the real solutions. The quadratic factors would come from the complex conjugates, because you could combine them together, and then the sum of the roots, the imaginary part, cancels out, and same with the product of the roots. And if you were to do it over the complex field, well then you'd just have n linear factors, and some of those factors would be complex. So what that means is, if you've got an odd-ordered polynomial, you must always have a real solution in there. Because if they're going to appear in conjugate pairs, the complex solutions must be an even number. And so if you have an odd polynomial, but an even number of solutions, there must be at least one real. Now there might be more. So let's have a look at this one. X squared plus 2x plus 2. Now one of the ideas I talked about before was, hey, all these quadratics we now can factorise using difference of two squares. Because we can complete the square, and so we get x plus 1 squared. That leaves me with plus 1, but I can make that a difference by looking at plus 1 and thinking of it as minus I squared, and so we get x plus 1 plus I, x plus 1 minus I. Okay, z to the power of 4 plus z squared minus 12. We can solve this like a quadratic, because you will notice the powers are going down by an even amount. So z squared minus 3, z squared plus 4. Well, if I use irrational numbers, the z squared minus 3 can be factorised using real numbers. Z plus the square root of 3, z minus the square root of 3. If I'm just dealing with real numbers, the z squared plus 4 would stay factorised like that. But it is an equation we're solving, so if I did it over the complex numbers, then the z squared plus 4 can also be factorised. Z plus 2i, z minus 2i. And then we can go and find our 4 solutions. Okay. If x minus a is a factor, then we know polynomial a equals 0. That's our factor theorem that we've seen. If it's ax minus b, remember then what we're going to substitute in is b divided by the coefficient of x, so b over a would be the solution. So 2x cubed minus 3x squared plus 8x plus 5. Now, fortunately 5 is a prime number, so that only gives us 5 and 1 to investigate. 2 though, well it's also prime, so we might have 5 over 2 or 1 over 2. So a logical first one to try would be, of course, 1 you would think would be logical. So let's try, let's see. It's a cubic. I know it's got a real one. We're trying to find it. Oh, of course, negative a half. Pick 1, jeez. No, negative a half would be the logical one to pick. And oh, what do you know? Turns out to be 0. So I know 2x plus 1 is a factor. And then I can work out the other factor by polynomial division or using a bit of logic. Remember the leading term times the leading term must give the leading term. The constant times the constant must give the constant. Now x squared minus 2x plus 5. Does that factorise nicely? Multiply together give 5. Add together give negative 2. Nah, there's nothing there, is there? So let's see what happens. Complete the square. Well, yep, we're not going to use real numbers because we've got a sum of 2 squares, which we can turn into the difference of 2 squares. And so we'll get x minus 1 minus 2i, x minus 1 plus 2i. So the first line would be if they asked us to factorise it over the real numbers. The last line if they've asked us to factorise it over the complex numbers. Alright, this time we've got a quartic. We're told it's got two rational zeros, which also means they must be real. Because remember, the sets of numbers, rationals live inside the real numbers. So we know there's two real ones, which means there must be two imaginary ones, because we know there's going to be four solutions all up. Find them and factorise. Okay, well 3 fortunately is a prime number, but we do have a coefficient of 4 out the front as well. So, logical first number to try would be 1. Yes, that's right, a half. Okay, so we try a half and it works. Oh, what do you know? So I know 2x minus 1 is a factor. Now, we've got to find another one. Let's find the cubic. So leading term times leading term, constant times constant. Let's find these missing terms. I wonder which I did first, the x's or the x squareds. Which would you go with first, the x's or the x squareds?
X squared.
Okay, let's see if I did. Oh, I went for the x's. Okay, so it must be 5x, and then when we look at it, how many x squareds do we need? By coincidence, we also need 5x squared. And there's your other real factor, minus 3 on 2. Sure enough, it did turn out to be 1 over 2 as well. So I now know 2x plus 3 is a factor. Okay, so the rational ones, half of minus 3 on 2. So I've solved the first bit. I've found the two rational ones. It wants us to factorise it over the complex field. Okay, I know 2 of the factors. The other factor, well, again, I can go leading term times leading term. You might find it easier to expand the first 2 out. It doesn't really matter whether you do or not, just be careful. So in this one I would have gone 2x times what gives me 4x to the power of 4, well that's x squared. The constant, minus 1 times 3 times what gives me negative 3, so I've got plus 1. I now just need to work out the x's. So how many x's do we have so far? Well obviously I'm not going to multiply the x squared by anything, that won't give me an x. So it must be 1 times 2x times minus 1, so that's minus 2x, and then I must go 1 times 3 times 2x, so that's another 6x. That gives, what did I say the first one was? Minus, so that gives me 4x. Yeah. We want 1x. So now I need minus 1 times 3 times what would give me x. Well, what do you know? It's 1. As I say, you might find it easier by expanding that out into a quadratic to work that one out. So x squared plus x plus 1, but it did say factorise over the complex field. So difference of 2 squares, and we get x plus a half plus root 3 on 2i, x plus a half minus root 3 on 2i. Notice we don't multiply by 2 and make this 2x and the other one 2x. Because remember, we're factorising the 4x to the power of 4. If I was to make those 2x plus 1 plus root 3i and 2x plus 1 minus root 3i, when I expand the whole thing out, I'd have 2x times 2x times 2x times 2x. If it was an equation, it'd be okay. Because we'd say equals 0 on the other side and it'd be fine. But when it's just factorising something, and I know it looks unusual having the fractions in there, but that's how I have to leave it. Alright, so the Cambridge exercise, 5A. Welcome back. Hope you had fun on your assessments. I'm sure you did.